The Car Crash Project by Shawnae, Hannah, and Alexa. After reading the problem and looking at the diagram, we were able to determine many factors such as velocity, mass, distance, and acceleration. Then we set up our momentum problem.
Slide 2. From the diagram and problem, we were able to determine the speed limit, distance, acceleration, and mass and velocity of the SUV and wagon. In order to find the initial velocity immediately following the collision of the SUV, use v squared equals v naught squared plus 2a delta x. And your initial velocity for the SUV should be 2.82 meters per second. In order to find the initial velocity of the wagon immediately following the collision, use the same equation, and your results for the wagon should be 12 meters per second. Slide 3. In order to determine the speed of the SUV before the collision, you should set up a momentum equation. The SUV representing block 1 and the wagon representing block 2. The mass of the SUV is 3,000 kilograms and the mass of the wagon is 2,000 kilograms before and after the collision. The velocity before the collision for the wagon is 0 meters per second, and immediately following the collision, it is 12 meters per second. The velocity of the SUV immediately following the collision is 2.83 meters per second. Multiply your masses and velocities in order to determine the speed of the SUV before the collision. Your speed of the SUV before the collision is 10.83 meters per second. To determine if the SUV was speeding or not, convert 35 kilometers per hour into meters per second, which should result as 9.70 meters per second. The SUV's speed is greater than the speed limit by 1.13 meters per second, which indicates that the SUV was speeding. Slide 4. To determine if the collision is elastic or inelastic, you must determine the kinetic energy before the collision and immediately after the collision. Use 1/2 mv squared in order to determine the kinetic energy. The kinetic energy before the collision for the SUV is 1,75933.35 joules, and the wagon is 0 joules. The kinetic energy after the collision for the SUV is 12,013.35 joules, and the wagon is 144,000 joules. Add your kinetic energies before the collision together, and your result should be 1,75933.35 joules. And your kinetic energies following the collision, and your result should be 1,56013.35 joules. The kinetic energy before the collision is greater than the kinetic energy following the collision, which means no kinetic energy was conserved, making this an inelastic collision. Slide 5. Creating the velocity time graph for the SUV before the collision, the SUV was moving at a constant speed. During the collision, the speed of the SUV slows down due to impact, and the collision continues slowing down after the collision until the SUV is no longer moving. The during slant is larger because the impact was greater, but it starts to slow down afterwards. Slide 6. Creating the velocity time graph for the wagon before the collision, the wagon was at 0 because it was stopped at a stoplight. During the collision, the wagon's speed accelerates due to the impact of the SUV, and after the collision, the wagon slows down until stopped. Slide 7. Creating the work energy graph for the wagon, the kinetic energy before the collision was 0 because it was not moving. The potential energy due to gravity is 0 because the height does not change, and the potential spring energy is 0 because no springs are involved. The kinetic energy after the collision rises due to the impact, and there is work done because of the impact of the SUV. Slide 8. Creating the work energy graph for the SUV, the kinetic energy before the collision is high because the SUV was moving. The potential gravity energy and the potential spring energy is 0 because the height does not change and because there are still no springs involved. The kinetic energy after the collision decreases because it loses kinetic energy when crashing into the wagon, and the energy is then transferred to the wagon. During the collision, the work is negative because the SUV slows down when crashing into the wagon. Slide 9. When creating the force time graph for an SUV, you must start by calculating the momentum, which is P equals mv. The mass before and after is 2,000 kilograms. The initial velocity is 0 meters per second because it is at rest, and the final velocity is 12 meters per second. This makes the momentum before 0 newtons and after 24,000 newtons. There was a positive gain in momentum, so the force time graph is an upward triangle. Slide 9. Creating the force time graph for the wagon, just like the SUV, you must calculate the momentum. The mass of the object is 3,000 kilograms. The initial velocity is 10.83 meters per second, and the final velocity is 2.83 meters per second, making the momentum 32.490 newtons before and 84.90 newtons after. This shows that there was a loss in momentum. Therefore, the force time graph is a downward triangle.